Hello everyone and welcome to this lecture on policy gradients. Now our previous neural network didn't actually perform very well, and this may be because we aren't really considering the history of our actions. Instead, we're really only considering a single previous action and its immediate reward, instead of a sequence of actions and how that may affect rewards in the far future. Now, this is often called an assignment of credit problem. Which action should actually be credited when the agent gets rewarded at time t? Should it be only the actions that happened right before it at t minus 1, or the entire series of historical actions? And a lot of times, this depends on the actual environment that your agent is working with. So if we have this problem of assigning credit to certain actions in the past, what we end up doing is we apply a discount rate. And this allows us to evaluate an action based off all the rewards that come after the action, not just the first immediate reward. So let's go ahead and describe how this works mathematically. What we end up doing is we choose a discount rate, and it's typically around somewhere between 0.95 and 0.99, and we'll explain how changing that closer to either 0 or 1 affects the actual calculation. But you essentially use that discount rate and apply a score to the action with this following formula. Let's say R is your total reward that gets returned back from the environment, and D is that discount rate, that 0.95 or 0.99 number. What you end up doing is you calculate a specific score for the action. This is actually different than the reward. This is a discount score that you are assigning that action. And it's calculated by the reward at time 0 when you actually immediately do that action. And then you add that to the next reward times your discount rate. Then the reward that comes after that times your discount rate squared. Then the reward that comes after that one times your discount rate to the power of 3, and so on, all the way until you get that final reward times the discount to the power of n. So you can see that future actions end up getting less and less because if you have something that's less than 1 and you keep squaring it, that becomes a smaller and smaller number. So the closer that discount rate is to 1, that means the more weight future rewards will have. The closer the discount rate is to 0, that means future rewards don't count as much as immediate rewards. And hopefully you can see that if you were to kind of plug in some numbers into this score formula. Now, choosing a discount rate often depends on the specific environment and whether actions have short or long-term effects. We can kind of look at our cart pull problem and decide that the action of moving left or right is probably only going to have a short-term effect. It's not really going to be important 50 actions into the future, whether or not you turned right or left. However, it probably has some importance a couple of actions into the future. So that will help you decide on whether you want a discount rate, as we mentioned before, closer to 1, meaning there's more weight on future rewards, or if you want it closer to 0, you're more concerned with short-term effects. So future rewards don't count as much as immediate rewards. And this is a careful balance that you're basically going to have to decide on based off the environment. And it's also something you can play around with to see what models perform better. So let's quickly diagram this formula. Again, what we're doing here is we're saying R is a reward, D is our discount rate, and we're ending up calculating a score by doing this summation multiplied by that discount rate as an action gets accounted for future rewards. Okay, so in this diagram we see here on the left-hand side we have our agent or our bot, and then it's going to perform some actions and get some rewards. And in this case, we're just looking at 3 time steps. So those arrows on the top indicate what actually happened in the environment. So the first action we perform is right, or we give the signal of 1, and the pull went up a little bit. It got straightened out. And for that, we get a reward of plus 10. Then because of that, the next action we happen to take is going left or entering 0, and again the pull goes up, so we get a plus 10. However, the next action going right ends up with the pull falling over, so then you get a negative 100. So what we want to do is analyze the score of that first right, and we're only looking at 3 time steps here. So typically what we did in the last neural network is we just assigned plus 10 to this action of going right. However, in a policy gradient situation, we want to learn if going right happened to have an effect in the future, such as when the pull fell over. So what we end up doing is we take the sum of those discounted rewards. So we end up saying the original reward, 10, plus the discount times the next reward, 10, plus the discount squared times the next reward, negative 100. And so we end up applying a score of actually negative 70.75 to that initial action of going right. So you can see here that we no longer treat this action as a positive, instead we have a negative. So this was a bad action to take due to the effect it had in the future. And that's the whole idea of a policy gradient, being able to take into account the rewards that happen in the future based off your initial action. So because of this delayed effect, sometimes good actions may actually receive bad scores due to bad actions that immediately follow a good action. So if we look back here, maybe it was really going left on that second action that caused the pole to fall over. So there is a delayed effect there, and good actions may receive some bad scores due to that. But to counter this, what we end up doing is we train over many episodes, and on average, good actions will end up receiving higher scores. Now we also then, in order to do this actual calculation, is normalize the action scores by subtracting the mean and dividing by the standard deviation. And these extra steps can actually significantly increase training time for complex environments. And you're going to notice that yourself when we actually code this all out and end up training over many episodes. As we get further and further along in future episodes or more playing of the game, you'll actually notice that the training time takes longer and longer. So implementing this gradient policy of Python and TensorFlow can be a bit complex, so what we're going to do is quickly go over the steps that we're actually going to be performing in our .py script. So the first one we're going to do is have the neural network play several episodes of this game. Then the optimizer is going to calculate the gradients. So typically what we've been doing is we call minimize on the optimizer, but this time, instead of minimizing it, we're first going to actually compute the gradients. And then we're going to compute each action's discounted and normalized score using the formula we just discussed. Then we're going to multiply that gradient vector by that action's score. And negative scores will end up creating opposite gradients when multiplied. So that allows the neural network to learn based off that policy gradient. And we also want to calculate the mean of the resulting gradient vector to then perform gradient descent. So because of the complexity of manually implementing this policy gradient technique with TensorFlow, I really encourage you to check out the extra resources for additional examples and explanations, because as far as the overall idea is concerned, it's pretty straightforward, but implementing it specifically with TensorFlow can be a bit complex. So just keep that in mind, take your time when we actually code along with it. Okay, in the very next lecture, we're going to hop to the text editor and code out this policy gradient. I'll see you there.